Today's quick lesson is how to create Lewis dot diagrams and basically what they're used for, how we can use them to determine the bonding of an element. Okay, well, so far we've talked mostly about the Bohr model, right? Bohr model shows me a lot of great information about atomic structure, right? I have protons, I have neutrons, I have electrons, I've got rings, I know where they are in the nucleus or around, so there's a ton of information showing up here on the Bohr model. Lewis dot is very simple. Okay, it shows two pieces of information about the atom of that element, and we use it to help determine how and with who that element is going to bond with. So a couple things about Lewis dot. First of all, Lewis dot diagram is used mainly to show the number of electrons in the outer energy level of an atom. Okay, so atoms have multiple rings. I'm focusing just on the electrons in the outermost ring. Now those electrons have a special name. We call those valence electrons. Valence electrons is a fancy name for the electrons in the outermost shell. And we all know that I can find the number of valence electrons or outer electrons looking at the element's group number. Now this is something that we've already practiced, so we should know that the group number is of course found going up and down on the periodic table, and we refer to those vertical groups as columns. So the groups are found up the periodic table, and of course the groups can range anywhere from 1 to 8. Now what we'll find out as we start looking at reactivity is that elements of the same group, of course, have the same number of valence electrons. And because they have the same number of valence electrons, they will therefore behave the same in a chemical reaction. Okay, so for instance, all the elements in group number 2 all want to do the same thing with their 2 valence electrons, therefore they will all react the same within a reaction. And that's where we're going to kind of get to. So there's 3 main rules that we want to know about when we look at our Lewis dot diagram. The first thing we want to do is look up the chemical symbol and the group number. And of course, both of these things are done using the periodic table. So the first one that we're looking at here is magnesium. If you can locate that on your periodic table to find the symbol and the group number, it's kind of on the left-hand side there. It is a metal. The symbol I need is the abbreviation for the element, capital M, lowercase g, magnesium. And the group number, again, looking vertically on the periodic table, group number 2. That's the only 2 pieces of information I need. Now once I have that information, I want to show where the valence electrons are on that element by placing some dots representing valence electrons around the chemical symbol. And when I do this, the first electron I want to make sure I put above the chemical symbol. Okay? So here we go, my Lewis dot. First thing I need is the symbol, Mg, and I place a dot above to start it out. There's my first dot, but of course I'm in group 2, which means I have 2 outer electrons, so I need to then continue around the side of the symbol. I want to spread them out, putting 1 on each side until each of the 4 sides is covered. Once I start filling up those 4 sides, then I can start pairing them up. This one only happens to have 2, so of course I'm only going to take up 2 of the sides, 1, 2. And that's really it. That's my Lewis dot diagram. By quick reference, I can look at this, know I'm dealing with Mg, because I can see the symbol, and there's 2 dots, therefore I am group 2 or 2 valence electrons. Let's try our next one here, oxygen. Find the symbol. Symbol is O. Looking up the column for group number is 6. So to create my Lewis dot diagram, I start with the symbol. I put the first electron above the chemical symbol. There's my number 1. Now I spread them out on each side until all 4 sides are filled. 1, 2, 3, 4. But I'm not done. I need a total of 6. I've only put 4 on my diagram so far. So now I can start pairing them up. And when I do so, I want to kind of put them together in cute little pairs. Okay, for the Bohr model, it wasn't specific where I needed to put the electrons. Here for LEWISdot, it is important. I want to space them in groups of 2 on each side. I don't want to spread them out evenly around the symbol. Carbon, symbol should be C. Group 4. LEWISdot, then of course, is my capital C. Starting at the top, working my way around. 1, 2, 3, 4. LEWISdot for carbon. Xenon. Chemical symbol, periodic table. This one's a little trickier to find. It's over in the noble gas section. Symbol Xe. Group number 8, as it is a noble gas. LEWISdot. I'm in group 8, so therefore I need 8 outer electrons, starting at the top. 1, to the side 2, 3, 4. I've gone all the way around. Now I can start to pair them up, now that each side is used up. Keeping them in nice little pairs on each side of my symbol until I reach 4. And remember, because there's only 8 groups, the max I can have is 8 valence electrons. I will never have more valence electrons than 8. So what's the point of this? How does this clue me in to reactivity? Well, got a couple examples of LEWISdot up here. We want to figure out, are these elements going to be gaining electrons when they go to bond with an element? Are they going to lose electrons when they go to bond with an element? Or do they not want to bond at all? Are they just going to stay the same and be good to go? Now when we're thinking of this, remember our key number that we're trying to get all electrons to is 8. Right? Each element has that magic number of 8 where they want to be stable and happy with 8. We know how many they have. We got to figure out how are they going to get to 8. Now we also need to know at this point that atoms are very lazy. They like to do the least amount of work possible. So knowing how many outer electrons they have is going to help us clue in to what they're going to do to get to that magic 8. So here's our friend chlorine up here. Of course, it has 7 valence electrons in need of 8. There's 2 ways it can get to that full happy place of 8 or 0. It can either gain 1 or lose 7. Again, atoms are lazy. They like to do the least amount of work possible. They'd rather deal with 1 electron than they would with 7. So chlorine is a gain element. It's going to gain 1 electron. Looking here at sodium. Sodium has 1 outer valence electron. It can either lose that 1 or gain 7. Again, atoms are lazy. They want to do the least amount of work possible. It's much easier for them to lose that 1 electron, get rid of it. This is a lose electron. Now, as these elements are gaining and losing, they're no longer perfectly balanced. They no longer have a perfect charge. For elements like chlorine here that gain electrons, they now have additional negative particles. Whenever an element gains an electron, it becomes a negative charge. On the opposite here, for our friend sodium, as it has lost electrons, now the protons are more numerous than the electrons. This now then becomes positive. See if you can figure out what oxygen and magnesium would want to do with their electrons. Oxygen, of course, has 6. Is it easier to lose those 6 or to gain 2? Again, elements being lazy, they want to deal with the least amount possible. These guys want to gain 2 electrons. By gaining 2 electrons, it will then become negatively charged. Over here, magnesium has 2 outer electrons. 2 outer electrons. Okay? Is it easier to lose those 2 or to get 6 more? Of course, dealing with the least amount of possible. It's going to lose those electrons and then become positively charged. Okay? Here's my last guy, xenon. He's got 8 outer electrons. Knowing that our magic number is 8, what does this guy have to do to get there? Kind of a trick question, right? He's already got 8 outer electrons. There's no reason for him to gain or lose. This guy is going to stay the same. He is good to go. He does not want to react with any other elements. Oops. Not reacting with any other elements. Again, just a quick description of LEWISdot and what they're used for. Check back